Welcome, curious cosmic explorers, to the Deep Dive. If you've ever found yourself just, gazing up at the night sky, feeling that ancient pull, and wishing you could see more, really unlock the universe's incredible secrets, well, you are absolutely in the right place today. We're taking a deep dive into the captivating world of telescopes. Now, this can often feel like a really complex subject, maybe a bit intimidating, full of jargon and just overwhelming choices. But our mission today is simple. Make it genuinely accessible. We're going to help you navigate those choices, understand the basics of these powerful tools. Drawing from an incredible resource, Telescopes 101, a beginner's guide by Sarah Lee from Number Analytics. We know you want to get informed quickly, yeah? Without getting bogged down, and that's what we're here for. Okay, let's unpack this amazing guide to stargazing.
Yeah, and what's truly fascinating here is how these instruments, fundamentally, they just use basic optical principles, but they reveal wonders far beyond what our own eyes can see. Understanding these principles, it isn't just about picking gear, it's really a gateway to understanding physics, our place in the cosmos. It's pretty profound stuff. It really helps to grasp the why behind it all before you put your eye to an eyepiece.
That's such a great point. So let's start there with the what.
Mm-hmm.
Our guide highlights that all telescopes, doesn't matter the design, they share one core purpose: to collect light. Collect and focus light from distant objects. Sounds simple enough, right? But the way they do it can be really different. And for beginners, yeah, this is where it can start to feel a bit much. But the source breaks it down really nicely into three main types. Knowing these helps a lot.
Absolutely. We're basically talking about reflector, refractor, and catadioptric telescopes. Each one works differently, and each one is better suited for different things. So first up, the reflector telescope.
Reflecting some mirrors, right?
Exactly. Uses mirrors. Imagine a big, curved primary mirror at the very back. Its job is to collect all that faint starlight. Then there's usually a smaller secondary mirror near the front that bounces the light sideways or back through a hole in the primary up to your eyepiece. Now, their big advantages? Well, generally, they're less expensive to make than lens telescopes of the same size. And crucially, you can make those primary mirrors really big.
And bigger aperture means more light.
Precisely. More light gathering. Fantastic for faint, deep space things. Think galaxies, nebulae, star clusters. Plus, they don't really suffer from chromatic aberrations.
That's the color fringing. Like a rainbow halo sometimes?
That's the one. Lenses can sometimes split light like a prism, causing that effect, but mirrors reflect all colors equally. On the downside, though, their open tube design means mirrors can get dusty, and they might need occasional realignment. It's called collimation. It's a bit more hands-on. Also, those big mirrors can make them heavier, maybe a bit bulkier to move around.
Okay, so if I'm dreaming of seeing those amazing nebulae, like the pictures you see, a reflector sounds like a strong contender. But you mentioned lens-based telescopes. What's the deal with those?
Right, that takes us to refractor telescopes. These are probably what most people picture first, like a classic spyglass shape. They use lenses. There's a big objective lens at the front to gather and focus the light, and then the eyepiece at the back magnifies that image. Refractors are known for giving really high contrast images, very sharp, minimal distortion, think crisp, clear views. And the optical tube is usually sealed, so they're super easy to use, very low maintenance.
That's good. So what are they best for?
They really shine for bright, detailed objects. The moon looks incredible through a good refractor. Planets, too, you can pick out details like Jupiter's bands or Saturn's rings, and splitting double stars, they give those pinpoint images.
Okay, makes sense. But there's always a trade-off, isn't there?
Usually, yes. The main one here is cost. High-quality lenses, especially large ones, are expensive to make. So, aperture for aperture refractors tend to cost more than reflectors. And while good designs minimize it, some cheaper refractors can show that chromatic aberration, that color fringing, especially on bright objects.
Right, so mirrors for faint deep sky stuff, lenses for sharp planetary views. That clarifies things a lot. But then there's this third type, Catadioptric. Sounds like a hybrid.
Exactly what it is. Catadioptric telescopes are a clever combination of both mirrors and lenses. They typically use a primary mirror, like a reflector, but they also have a lens element, a corrector plate at the front. This corrector plate helps focus the light and corrects for optical errors or aberrations.
So kind of the best of both worlds.
That's the aim. The big advantage is that they pack a lot of optical power into a very compact, portable tube. This makes them really versatile, great for deep space, great for planets. They give high-quality images across the board. They actively correct for issues that might pop up in simpler designs.
Sounds ideal.
Yeah.
Especially if you want to dabble in everything or need something easy to transport.
They are really appealing for those reasons.
Yeah.
The main drawback, well, that complexity usually comes with a higher price tag. They tend to be the most expensive of the three types. And if something does go wrong, maintenance can be a bit more involved because of the intricate design. So yeah, summarizing, reflectors are mirror-based, refractors are lens-based, and catadioptrics are that clever mix.
Okay, that breakdown is super helpful. It really clears up the basic designs. But then comes the next hurdle, right? Actually choosing one. You look at all the options, the specs. It can feel, well, pretty daunting for a beginner. So what are the really crucial things to focus on when you're trying to pick one out?
Yeah, this is where the source guide really shines. It helps you cut through the noise. It boils down to a few key factors. Aperture and magnification, what you actually want to look at, and something often overlooked, the mount and tripod. Let's tackle aperture and magnification power first. Aperture is simply the diameter of that main mirror or lens. Basically, how big is the telescope's eye? And this is really important, probably the most important spec.
Why is it so critical?
Because a larger aperture gathers more light. Think of it like opening window blinds wider. More light means brighter images, and crucially, higher resolution, more fine detail. It's like going from standard definition to high definition TV.
Got it. More light, more detail.
Exactly. Now, magnification. That's determined by the eyepiece you plug in. Shorter focal length eyepiece equals higher magnification. Simple ratio. But, and this is a huge aha moment, the guide stresses for beginners chasing the highest magnification number is often a mistake.
Oh, why is that? I thought more zoom was always better.
Not necessarily. If your aperture isn't big enough to gather enough light for that high magnification, all you get is a bigger, dimmer, blurrier image. It's called empty magnification. It's useless, really disappointing.
Ah, so you need the aperture first to provide the light and detail? Then magnification makes that detail bigger.
Precisely, you've got it. The guide even gives some useful benchmarks, like a 60-80mm aperture scope. It'll probably give you nice, clear views around 50x to 100x magnification. Step up to 100 and 150 millimeters, and you might reasonably use 100x to 200x. Get into the bigger 200 to 250 millimeter range, and maybe you can push 200x to 400x on good nights if the aperture provides a bright enough image to start with. So don't just look at the X number, think about the quality of the view. Next key factor, what do you actually want to observe? Your goals should drive your choice. What calls to you most in the night sky?
Makes sense. Tailor the tool of the job.
Exactly. If you're dreaming of those faint galaxies, nebulae, star clusters, deep space stuff, you'll generally want a reflector or a catadioptric, probably with as large an aperture as you can manage and afford to capture that faint light. But if you're more fascinated by the moon's craters, Jupiter's cloud belts, Saturn's rings, or splitting tight double stars, then a good refractor or a catadioptric known for high-quality optics and sharpness might be a better fit.
Okay, so thinking about my target objects helps narrow it down.
Definitely. And finally, mounts and tripods. Don't underestimate these.
Right, gotta hold the telescope steady.
Critically steady. A sturdy mount and tripod are absolutely essential. It doesn't matter how good your telescope's optics are if the whole thing is shaking. Imagine finding a faint galaxy, and then the slightest breeze or even focusing makes it jump all over the place. It's frustrating.
Yeah, that would ruin the experience completely.
Yeah, it really does. The source mentions two main types of mounts. Altazimuth mounts are simpler. They move up, down, altitude, and left, right, azimuth. Pretty intuitive, great for casual viewing, just pointing and looking, but tracking objects as the Earth rotates can be tricky, needing constant nudges in both directions.
Okay, simple, but maybe not ideal for longer looks.
Right. For that, you have equatorial mounts. These are tilted to align with the Earth's axis. They look more complex, and setup takes a bit longer initially. But once aligned, they can track celestial objects smoothly across the sky with just one slow-motion control or motor. This is almost essential for things like astrophotography or really studying an object over time.
Ah, so more complex setup, but better tracking.
Exactly. And regardless of the mount type, the tripod itself needs to be solid, heavy enough, well built enough to dampen vibrations. Stability is absolutely key. A powerful telescope on a flimsy mount, it's like, well, like putting a race car engine in a shopping cart. All potential, no performance.
Huh. Great analogy. Okay, that makes perfect sense. Stability is crucial. So let's say you've navigated the choices, you've picked your telescope type, aperture, mount, and the boxes arrive. What next? Getting it all set up and actually using it for the first time can seem like the next big hurdle, maybe a bit intimidating.
It can feel that way, yeah. But the guide really emphasizes patience and practice. It's not a race. And it breaks down the process into manageable steps. First is assembling and aligning. Step 1. Read the manual. Seriously. Follow the manufacturer's instructions carefully. Don't just, wing it.
Good advice for anything, really.
Isn't it just? Then you'll need to align the telescope's optics. For reflectors, this is collimation. For others, it might just be ensuring everything is seated correctly. The manual will guide you. This makes sure all the optical parts are working together perfectly. And finally, adjusting the focus knob to get that nice, sharp image. Think of it like tuning a guitar before playing. Precision in setup gives you harmony in the viewing.
Okay, assemble carefully, align properly, focus. Makes sense. But then there are all the controls. Focusers, eyepieces, mount knobs.
Right. Step 2 is getting familiar with the controls and features. Take some time, even during the day, just to understand how everything works. How does the focuser move? How do you swap eyepieces? What do the mount's slow motion controls or locks do? If you have a fancy computerized go-to mount that finds objects for you, well, you definitely need to learn how to set that up and use it.
So just play around with it a bit.
Absolutely. Practice. Don't be afraid to experiment. The more you handle it, the more intuitive it all becomes. Muscle memory helps. And that leads to the final stage, practicing observations. The guide gives great advice here. Start simple. Don't try to find the faintest galaxy on your first night out.
Aim for the easy stuff first.
Definitely. The moon is perfect. It's big, bright, easy to find, and full of amazing detail, even with modest magnification. Bright planets like Jupiter or Saturn are also great starting points. Once you're comfortable finding those, then practice using different eyepieces. See how changing magnification affects the view. Get a feel for what works best for different targets. And then, gradually, you can start hunting for slightly more challenging deep space objects like star clusters or brighter nebulae. It's a journey, Discovering the sky, but also discovering what your telescope can do.
That sounds like a really sensible, encouraging approach. Takes the pressure off. Now, we've talked about the physical telescope, setting it up, using it. But you mentioned earlier there's this underlying science, the physics and math behind it all. Our guide touches on this too, right? Not necessarily to make us do complex calculations, but to appreciate the design.
Precisely. You don't need to be a mathematician to use a telescope, but understanding a couple of the core principles really deepens your appreciation for why things work the way they do. And it helps explain why certain features, like aperture, are so important. The first concept is resolution. We touched on this. Simply put, it's the telescope's ability to distinguish fine details, to see two close stars as two points, not one blob.
The sharpness, basically.
Kind of, yeah. It's about the level of detail you can actually discern. And the physics behind it is fascinating. There's a formula, the Rayleigh criterion, if you're curious. But the key takeaway is that resolution is fundamentally limited by the wavelength of light you're looking at, and, crucially, the diameter of your telescope's aperture, D.
Oh, aperture.
It always comes back to aperture. A larger aperture, a bigger D in the formula, directly results in better theoretical resolution. A smaller angle it can resolve. It literally allows the telescope to see finer details. So that formula. It shows us why aperture is king for detail. It's not just opinion, it's physics.
Wow, okay. So the math backs up the bigger is better for detail idea. What else?
The other key one is magnification power. We talked about how it depends on the eyepiece. The formula is actually pretty simple. Magnification M equals the focal length of the telescope divided by the focal length of the eyepiece.
Okay, so telescope focal length, eyepiece focal length equals magnification.
You got it. So if you have a telescope with, say, a 1,000 millimeter focal length, and you use an eyepiece with the 25 millimeter focal length, your magnification is 1,025 equals 40x. Swap in a 10 millimeter eyepiece. Now it's 1010 equals 100x magnification.
Ah, so a smaller eyepiece focal length number means higher magnification.
Exactly. It's a simple ratio, but understanding it is powerful. It lets you choose the right eyepiece to get the magnification you want.
Yeah.
Always keeping in mind that practical limit we talked about. You need enough light and resolution from the aperture to make that magnification useful.
This has been fantastic. A real deep dive into telescopes, demystifying them piece by piece. We've covered the main types of reflectors, refractors, catadioptrics. We've looked at how to choose one. Focusing on aperture bigger is generally better for light and detail. But knowing that just cranking up magnification isn't always the answer. Quality over quantity. And we've got a clear path for setup and those crucial first observations. So what does this all mean for you, the listener, the aspiring stargazer? You're much better equipped now.
Absolutely. That knowledge really is empowering. It takes the guesswork out of it. You know, lots of beginners ask that fundamental question, okay, but what's the best telescope for me to start with? And our source, Telescopes 101, actually offers some practical advice here. It suggests that a good starting point is often a refractor or a reflector with a moderate aperture, maybe in the 60 millimeter to 100 millimeter range.
Kind of a sweet spot for beginners.
Seems to be. Good quality models in that range might cost, say, somewhere between $500 and $1,000. They offer great views, a good learning experience, without being overwhelmingly complex or expensive. But this leads to a final important question for you to think about. What exactly do you want to achieve with your first views of the night sky? Are you drawn to wide, sparkling fields of stars? Or do you want to zoom in on the pinpoint details of a planet? Or maybe try a bit of both. The universe is definitely waiting. And now, hopefully, you have a much better map to help you choose your window.